Listen to part of a lecture in a meteorology class.
Okay, as we begin to study clouds, we're getting into one of the big unknowns in meteorology. And that's the question of why some clouds produce rain and some don't. Now, one potential benefit of figuring this out is that we should be able to improve our ability to produce rain artificially, like by seeding clouds. Now, you probably already know how clouds form. Jennifer?
Basically, warm air rises. As it rises, it cools. And as it cools, the moisture it carries condenses, forming clouds. It's probably more complex than that, though.
A bit, but it's a good basic explanation. As you said, air rises, carrying water molecules with it. Remember, water molecules are virtually everywhere, even though we can't see them. Air temperature drops with altitude. And as the rising air cools, the water molecules condense to form droplets by attaching to microscopic particles floating in the air. When there are enough droplets grouped together, they become visible as clouds.
And the drops, they keep condensing, getting bigger and heavier, right? Until they're too heavy to stay up in the cloud and they fall out as rain.
Sort of, but, well, not exactly, or not always. See, it all depends on size. We're talking about very small sizes, micrometers or microns. They're the same thing. That's about 1/1000th of a millimeter. Definitely much smaller than the human eye can see. Anyway, when we talk about the size of water droplets in clouds, there are two important measurements. The first is about 10 micrometers. When droplets form, they can grow about 10 micrometers in just a few minutes. Unfortunately, quite often, these droplets just stop growing. Sometimes they grow, sometimes they don't, and as I said, we don't know why. In the first stage of droplet formation, until the droplet reaches that 10 micrometer threshold, condensation works pretty well. But after that, it becomes a very slow process. It would take days for a raindrop to form using just condensation. But once a droplet reaches 40 micrometers, the problem of growth disappears. That's our second important number, 40 micrometers. At that size, droplets have a good chance of colliding with one another and sticking together. We call the process collision and coalescence. And once this process begins, you get rain pretty quickly. So the big question is, how come some droplets are able to grow to 40 micrometers and others aren't? There are a number of hypotheses to explain raindrop formation, but none of them offers a complete solution. One hypothesis, the turbulence hypothesis, suggests that air movement inside clouds may actually help droplets collide more quickly and more efficiently. Some meteorologists think that the violent air movement that is turbulence may actually reduce the size of droplets necessary for collision and coalescence to occur. That under the right conditions, this process could begin with droplets closer to 10 micrometers than to 40. But as I said, this seems to be only a partial answer. Marcus.
What about large particles? Because sometimes water molecules attach themselves to relatively large particles in the air.
That's another hypothesis. If water molecules attach themselves to these larger than average particles, they might grow to 40 micrometers much more quickly. That could mean that on days when lots of large particles are present in the air, it might be more likely to rain. But there is little evidence to support this idea.
Is there any research out there that's moving towards an answer?
Well, there was an exciting project a few years ago. It was a rather extensive study performed in areas around the Caribbean Sea. The idea was to collect lots of data about the size and movements of water droplets in clouds, and use that information to try and figure out what's actually happening inside of them. Researchers are still going through the data, so we don't have any answers yet. But researchers did make one unexpected discovery. They saw clouds forming out of the leftovers, the debris of old clouds. That was a new one to us. Now, it could be possible that this recycling initiates rainmaking, as droplets from the old cloud combine with the newly forming cloud to grow into droplets large enough to fall as raindrops. But while we have observed new clouds forming out of old ones, we haven't yet seen them produce rain.
What does the professor mainly discuss? According to the professor, what often happens to water droplets in clouds when they reach a size of 10 micrometers? What does the discussion of the collision and coalescence process help explain? According to the turbulence hypothesis, what is the effect of increased turbulence inside a cloud? What does the professor imply about recent research conducted in the Caribbean Sea? Listen again to part of the lecture, then answer the question.
But after that, it becomes a very slow process.
Why does the professor say this?
It becomes a very slow process.